Taking a look at mechanical energy, this combines both our kinetic energy and potential energy. So when energy is transferred to an object, it can cause a change in both the kinetic and potential energy simultaneously or at the same time. For instance, a ball thrown upward has kinetic energy because of its motion in the air, but it also has potential energy because of its position above the surface of the earth. Since kinetic and potential energy are so closely related, in so many different situations, they are combined as a type of energy called mechanical energy, or EM, which is defined as the energy due to the motion and the position of the object. So the formula for this is mechanical energy is equal to kinetic energy of the object plus its potential energy. So in a formula with variables, EM is equal to EK plus EP. So this means that the sum of the potential and kinetic energy of a system is always the same throughout its situation. So for instance, back to the ball for a second here, as it is moving upward, it has kinetic energy. But I know that as I throw a ball up into the sky, it slows down until it reaches its maximum height. At its maximum height, it's actually stopped. It's not moving. The speed of it is 0. So at the bottom of its toss, it had very little height. It had its minimum height. And the moment it left my hands, it had its maximum speed. Okay. And then again, it started to slow down as it reached its maximum height and 0 speed. So together, at the top of its toss and the bottom of its toss, it has the exact same amount of mechanical energy. Throughout its toss, it's just transferred from kinetic energy going to 0 and our potential energy increasing. So we use that idea in a bunch of different situations here. So for example, a seagull flying horizontally at 8 meters per second carries a clam with a mass of 300 grams in its beak. Calculate the total mechanical energy of the clam while the seagull is 30 meters above the ground. So in this case, we are looking to calculate the total mechanical energy, knowing that this seagull has both potential energy due to its height above the ground, this clam has potential energy due to its height above the ground, but it also has kinetic energy because it is in motion. So let's list out the information we were given here. So a seagull flying horizontally carries, at a speed of 8.00 meters per second. There should be a space here. Carries a clam with a mass of 300 grams in its beak. Calculate the total mechanical energy of the clam when the seagull is a height of 30 meters above the ground. So the equation we're using here is EM is equal to EK plus EP. Now, we know that EK is 1/2 mv squared, and EP was mgh. So I've just subbed those in for the variables EP and EK. Okay, so EK was equal to 1/2 mv squared and EP was mgh. Okay, going back to our information for EP, mass must be in kilograms, and we have a mass in grams currently. So to go from grams to kilograms, we need to divide by 1,000. because there are 1,000 grams in 1 kilogram. So that gives us 0.300 kilograms. So we have the correct units for mass. Gravity is always 9.81 meters per second squared. So we have that value, and we have the height above the ground. So we can calculate the potential energy of the clam. Looking at EK, we also have mass in kilograms, so we're good. And we have the speed in meters per second. So we are able to completely calculate the right-hand side of our equation here, just subbing in the information we have to calculate the total mechanical energy. All right, so EM is equal to 1/2 the mass in kilograms times the speed in meters per second, and we're going to square that value. We're also going to add to that our potential energy. So the mass, 0.300 kilograms, multiplied by gravity and height. So 9.81 meters per second squared, and our height was 30 meters above the ground. So I calculated each of these numbers individually. So I immediately calculated what I got for the kinetic energy here. So with that, I ended up with 9.6 joules, a very small number. And then I calculated what I got for the potential energy of the clam. So that value was 88.29 joules. So I'm just going to add those two values together to get 97.89 joules. And that is our total mechanical energy for the clam. At the end of the day here, we need to do significant digits. Everything seems to have 3 significant digits in our question, so we should round our final answer to 3 significant digits as well. That would be 97.9 joules as a final answer. So this just looks like a lot of math. If you wanted to individually calculate the kinetic and the potential energy and then simply add those values together, you can as well. So you can break it down stepwise. All right, let's continue on. A 55 kilogram high jump athlete leaps into the air in an attempt to clear the bar. At the top of the leap, the athlete has a total mechanical energy of 3.00 times 10 to the 3 joules and is moving at 8.33 meters per second. Calculate the gravitational potential energy of this athlete. So let's list out what we have for information and decide what we're trying to look for and find a formula that will work for us. So we have a mass, 55.0 kilograms. And at the top of the leap, they have a total mechanical energy of 3.00 times 10 to the 3 joules. And they are moving with a speed of 8.33 meters per second. We are looking to just calculate the total potential energy of this athlete. So let's write out our formula. EM is equal to EK plus EP. And we are looking to solve for EP in this case. So I need to expand EK. We know that EK was equal to 1/2 mv squared. Therefore, we can solve this because we have a mass in kilograms and we have a speed in meters per second. So why don't we break this down into steps for this question and solve for our final answer. So what I'll do is I'm going to solve for EK first. So EK is equal to 1/2 55 kilograms times the speed 8.33 meters per second, all squared. When I calculate that, again, don't forget to actually square this number. When I calculate that out, I got 1,908 joules for the kinetic energy. What we can do now is we can go back to our EM is equal to EK plus EP formula and sub in what we know. We could sub in what we know, or we can rearrange first. It's up to you. So I think I will rearrange first. I need to rearrange this equation to solve for EP. So EM equals EK plus EP. I'm going to subtract EK from both sides. And I'm left with EP is equal to EM minus EK. So I'm going to sub in the values for EM, which we have here, and EK, which we just calculated, to solve for EP. So EP equals 3.00 times 10 to the 3 joules. Take away 1,908 joules. And I got 1,092 joules. At the end of our question, looking at significant digits, it appears that every value in our question has 3 significant digits. So I would report my final answer in scientific notation, moving my decimal place 3 times. So I would report it as 1.09 times 10 to the 3 joules. The law of conservation of energy states that the total amount of energy in a given situation remains constant. So energy can be converted from one form to another, but the total amount of energy never changes. That means that EM is constant. Hence what it just says here. The amount of mechanical energy in a system is constant. The only thing that can change is the proportion of energy that is kinetic or potential at any time. So what this means, is that in a system, the amount of energy present is always constant. So this could be labeled as EM, the amount of mechanical energy in a system. The only thing that can change is the proportion of that energy that is potential or kinetic. So what this little diagram says is that at any time, if I add up the amount of energy here, the value that is kinetic and the amount that is potential, it will always be the same as the mechanical energy total. So if I have lots of kinetic energy and just a little bit of potential, it will still equal the same as if I only had all potential, no kinetic, or a 50-50 split. So it doesn't matter where you are along this trajectory. If you added up the values of potential and kinetic, they will always equal the same value of EM. So what this means is that potential energy can be converted into kinetic energy, and kinetic energy can be converted back into potential energy. So this arrow shows that potential energy can change into kinetic, and kinetic can change into potential. So what we will say then is that the change in potential energy is equal to the change in kinetic energy. So whether that change was I am losing potential energy, meaning I am gaining kinetic, or I am losing kinetic and gaining potential. So we'll use that idea moving forward here. Bart Simpson and his skateboard have a mass of 55 kilograms. Bart is at the top of a hill that has a vertical height of 22.5 meters. Assuming all of his potential energy at the top of the hill becomes kinetic energy at the bottom of the hill, how fast is Bart traveling at the bottom of the hill? So again, Bart had potential energy, specifically gravitational. Oops, spelling, gravitational. And that was converted into kinetic energy. So the loss of his potential energy was equal to the gain of his kinetic energy in this case. All right, let's list the information we have. So Bart has a mass of 55 kilograms. The hill has a height of 22.5 meters. Assuming all the potential, how fast is Bart traveling at the bottom of the hill? Now, this doesn't look like a lot of information, so let's look at our equations. So EP is equal to EK here. Remember that EP is mgh, and EK was 1/2 mv squared. So let's see if we have enough information to solve for V in this case. We have a mass in kilograms. We always have G, that's 9.81 meters per second squared. We have the height of the hill. Half is just a constant, and we have the mass. So we should be able to solve for V. So in this case, to get V by itself here, I'm going to multiply both sides by 2 initially to cancel out the 1/2. 1/2 times 2 is 1. I'm also going to divide each side by mass to cancel out the mass here. Mass actually cancels on both sides. So what we are left with here is that 2 times G times H is equal to V squared. Notice that mass cancels out when potential energy is directly equal to kinetic energy here. Okay, so we actually don't even need Bart's mass. We could calculate this without a mass. All right, to wrap this up, we need to square root both sides to get just V. So V is equal to the square root of 2 times G times H. So let's sub in what we know. So 2 times 9.81 meters per second squared times H, 22.5 meters, and square root that. Note that the value of G is not squared, it is simply its unit, so I am not squaring this number here. All right, calculating that out, I ended up with a value of 21.0 meters per second. And that looks good for significant digits. There are 3 here and 3 here. An average force of 100 newtons is required to pull back a bowstring a distance of 0.5 meters. The bow is aimed vertically, meaning that when they release it, the arrow is going straight up. What is the work done on the bow? So, listing out your information, we have a force of 100 newtons. We have a distance of 0.500 meters, and we are looking for work. Work is equal to force times distance. So subbing into that formula, work is just equal to this 100 newtons times 0.500 meters, and we end up with 50.0 joules. And again, significant digits. This is 3. Remember that leading 0 doesn't count. This one's 4, but I still have to report my final answer to the lowest number of significant digits. So how much potential energy is stored on the bow? We did work to pull back the string on the bow, and that work was transformed into potential energy. In this case, it's elastic potential energy. So the work done was transformed into elastic potential energy. Therefore, in this case, we could say that work done was equal to the change in potential energy, elastic. Therefore, the work done here, the potential energy stored in the bow now is 50 joules. How much kinetic energy does the arrow have the instant it is released from the bow? So when it is released from the bow, that potential energy, the elastic potential energy, is transformed into kinetic energy. So EP, elastic, is transformed into EK. Therefore, we can say that EP, elastic, potential energy elastic, is equal to EK. Therefore, the amount of kinetic energy this arrow has is 50 joules. What will be the potential energy of the arrow at its highest position in its flight in the air? So this arrow is going to travel upwards until it has no more kinetic energy. All of that kinetic energy is changed into its height, its potential energy. So the last one we see here is that all of its kinetic energy was transformed into potential energy, but specifically gravitational potential energy. So EK is equal to EP, gravitational. Therefore, we once again have 50 joules. So energy is conserved throughout the loading and firing of an arrow in a bow. Energy is also conserved in a pendulum, and so I wanted to take some time to look at that idea here. So if we draw our pendulum here, the pendulum, let's say, is started at the left, and that is above some sort of surface. This pendulum has a particular height, h, above the surface, and at this point it's like your hand is holding it. It does not have any kinetic energy because it's not moving. So the speed of the pendulum is 0, therefore the amount of kinetic energy it has is 0. This pendulum is as high as it will be throughout its swing. Remember, the pendulum is going to swing downwards here, so the height will decrease. So it's at its maximum height here. Therefore, it has the maximum amount of potential energy at this moment. Now, this pendulum, of course, will swing. And let's look at when the pendulum is in the middle. So it's now at a lesser height. So I'm going to call this height 1, and I'm going to call this height 2. So height 2 is less than height 1. It's not as high above the ground now. So it has the lowest amount of potential energy at this point. Okay, because remember, EP is equal to mgh. So it has the lowest amount. EP is its minimum amount throughout its swing now. It's at the lowest height. However, this pendulum is traveling at its maximum velocity or speed at the bottom of its swing. It's gained momentum to the bottom, and now as it would swing up from this point, it's going to slow down due to gravity. So if its speed is at its maximum, it has its maximum amount of kinetic energy at the bottom of its swing. Now this pendulum continues to swing. I'm going to try and keep these moderately consistent in height. We are back to height 1, its highest point. And once again, this has stopped. Therefore, EK is 0, or its minimum again. Because it's got its maximum height again, it has the maximum amount of potential energy it could have throughout its swing. So we see this conversion of energy from we have only potential energy and no kinetic. We start to gain kinetic and lose potential until we are at this point where it has its maximum amount of kinetic energy and its minimum amount of potential energy. It will continue to swing and slow down until its speed equals 0 again, but it once again has its maximum potential energy. It will then continue this cycle back and forth, conserving energy throughout. Now, of course, this is in a world without resistance and other factors like friction at the top of our pendulum swing and air resistance as it's traveling. So this is a perfect world, but this shows the conservation of energy. If we were in a perfect world, the pendulum would never stop. It would continue to reach the exact same height on each side, no matter how long it continued to swing. Our last question here, a pendulum with a mass of 405 kilograms reaches a maximum speed of 6.9 meters per second at the bottommost point in its path. What maximum height will it reach? So in this case, at the bottommost point in its path, it has the maximum amount of kinetic energy. That kinetic energy will be converted into potential at its maximum height. So we can once again say that EK will transform into EP. Therefore, EK is equal to EP in this case. So listing our variables, the mass is equal to 405 kilograms, and it reaches a speed of 6.9 meters per second. What is the maximum height? We always have gravity, so I'll just write it out here before we check our variables because I know I'm going to need it when potential energy is involved. Okay, so EK is equal to EP. Therefore, we know EK is 1/2 mv squared and EP is mg and h. To solve for h, I'm going to divide both sides by m times g, and that will cancel m and g here. And I'm going to divide, of course, this side by m and g. Notice that once again, m cancels on both sides, and I'm left with 1/2 v squared divided by g is equal to the height. So subbing in our information here, just checking before we do. Gravity is of course in its proper units. Speed is in meters per second, so we are good to go. Once again, I don't actually need mass when I equate potential and kinetic energy. Okay, so height is equal to 1/2 times v squared, so that's 6.9 meters per second squared. And we will divide that by 9.81 meters per second squared. Once again, noting that we actually need to square the number for speed, but we do not square gravity. The square here is from its unit. I end up with a final answer of 2.4266. And that would be in meters. That's the unit of height. Remember, significant digits. In this case, the only value from the question that we actually used was the 6.9 meters per second. And that has two significant figures. So I'm going to report my final answer as 2.4 meters. Some practice for you in your textbook. Take a look at page 188. Number 2, 4, 5, 6, 7, 9, and 10. If you only intend on doing a few questions today, I would highlight number 2, 5, 6, and 10.